In this video, I want to talk about not how to compute a cross product, but what it actually means geometrically, what it represents. So this was a problem we did in the previous video where it came out to be 0, 0, negative 22. Now, to think about this more geometrically, we need the right-hand rule, and here it is. And it uses actually the right hand. I got this from OpenStax. Now, essentially how it works is when my U is going to V, it's going in this direction. You can think of your fingers curling like you see in this hand here, in this picture. And if it's going in that direction, that means my vector is going up. So now what I want us to do is look at this problem that we did previously. And I want us to see what that means. So if we're going in this direction, right guys? We're going in that direction, and I think about my hand, that means my thumb is actually going to be pointing downward. And not only do we find a vector in that direction, but that vector is actually orthogonal also to both of those vectors. So that's kind of what's interesting about that too, is not only does this cross product find a vector in the a different direction, that direction is actually orthogonal to the other two directions, or the other two vectors. So that's how we can think of the cross product. So when I find a cross product, I'm finding a vector that's orthogonal to the other two vectors. Okay, and that's what's most important here. And we use this idea quite a bit in some really cool ways. So now if I think about these two vectors here, this U here and this V here, now what we're going to do is we're just going to graph those. Now if I think of those two vectors, I have vector 3, 5, 0 and 2, negative 4, 0. Notice my values for my Z are both 0, so that tells me it's on the XY plane. So it's on this plane right here. So what we're going to do is we're just going to graph those vectors. So 3, 5, 0 is going to be, I go up 3 in the X direction, so that'll be here. And then I go to the right 5. So that's going to be the vector. So there's my vector U. And then my vector V, I'll do in another color here. I'll do green. We haven't done green in a while. And that's going to be 2, negative 4, 0. And we can see here that when I create that vector, I'm going from U to V. Now, if I was going in the other direction here, kind of like our picture with this right hand in it actually, because I'm curling this way, that means it goes upward because my thumb would be pointing upward. But since now, if I look at this picture in comparison to this right hand rule idea here, I'm actually going in a downward direction because my hand is actually curling in that direction, the opposite direction. So that means it would be pointing downward. Now look at the answer for this one. The answer for this one was 0, 0, negative 22. And if I graph that vector is going to be running straight down this way on the z-axis. So because my x and y are both 0, which means that we know these are going to be perpendicular because both of these vectors are actually on the XY plane. So that's why we got the answer that we got here. Very nice. I just kind of wanted you to understand what this cross product was that we're actually finding here. We're finding a vector that's orthogonal to the other two vectors. Sometimes we'll have directions that ask us to find vectors of this sort, or find one that's perpendicular to another vector. And this is one way we can accomplish that using a cross product. So now when we look at the properties of these cross products, what we'll see is that we have a not quite commutative property here, which this hopefully makes sense to you now too, because of what we've seen with the right-hand rule. So U cross V is not equal to V cross U. It's actually equal to the negative of V cross U. And that comes from just taking a look at the example that we had over here. So remember that when I was going U to V, which was here, then that was clearly going to be in an upward direction. So that's going to be a positive direction. So it'd be a positive vector in a sense. And when I go the other direction, like I did with this problem here, we've seen that it actually my thumb went downward here. So that vector was going to be in a downward direction. So the sign changed. And initially, if I was going in a downward direction, when I did the cross product of it, when I'm taking the cross product of it, and the cross product is a downward direction, if I reverse the order, I'll see that it's going to be in the positive direction. So essentially, that's what that means then. So if this turned out to be a negative value in a negative direction, or just straight downward, let's say, then this one, when I negated it, would actually be in an upward direction. So that's essentially how that's working. So it's not going to be a commutative property. They actually call it anti-commutative property. And that's something that's a little interesting. And then we also have all these other properties that just kind of hold here, other than that commutative property. So we have a distributive property, which is here. We have a multiplication by a constant, which, okay, that's no big deal. Cross product is just a vector. So when I times it by a scalar, it's not going to matter either way. When I cross u with a zero vector, I get 0. And hopefully that makes sense to you. For the simple fact, remember, the zero vector is just going to be 0, 0, 0. And no matter how I times that, I'm always going to end up with just a bunch of zeros back, even when I think of it in terms of the cross product. Doesn't matter what these values are. When I cover up this one, I'm still going to get 0. When I cover up the middle, I'm still going to get 0. When I cover up the last, I'm still going to get 0. So hopefully you can see that clearly. So that's not an issue. V cross V is 0. Now that's kind of interesting there. But go through it, have fun with it. So those are just the properties that we're actually going to be dealing with too with these cross products.